Hi everyone, and welcome to the fourth and final video going through some past exam questions on transition metal complexes. Slightly different question to start with here. This is a long question here that's quite tricky, but it starts off with this nice easy bit. We've seen questions like this before. Just wants us to write the electron configurations of a chromium atom and a chromium ion. Okay, so we look up chromium on your periodic table, and chromium is here, so it's going to end with 4s2 3d4. But we need to remember that chromium is the exception. Right, of course, they've chosen the one that's the exception to put in the question, right? That's, typical exam board. So let's just be careful with this then. Write this out properly. Again, I think I've said this on previous videos. Don't try and shorten it down. With the noble gas, I'd write it out properly. 3p6. It's not going to be 4s2, it's going to be 4s1. 3d5. And we can also do a check, can we just make sure these numbers add up? 2, 4, 10, 12, 18, 19, 24. Yeah, 24. Okay. So that's always worth checking to make sure you haven't messed that up. Chromium 3 plus then is going to lose 3 electrons from here. And then remember, it's going to lose the 4s electron first, and then 2 from here. So this bit would all be the same. We're going to lose the 4s electron and then lose 2 more, so it'll be 3d3. Okay. Right, this question then, this is a bit more of a significant undertaking here. It's an 8-mark question, look, so there's a lot to do here. Okay. Right, what does it say? Compound A is an orange ionic compound of chromium with a percentage composition by mass of this. Okay, so as soon as I see this, so going, right, we're going to be doing empirical formula here, right, with these percentages. It doesn't have water of crystallization. Okay, well, that's good. That's one less thing to worry about. On gentle heating, compound A decomposes to form 3 products, B, C, and water. B is a green oxide of chromium with a molar mass of this. C is a gas, a room temperature pressure. Each cubic decimeter has a mass of 1.17 grams. Okay. Show all you're working out. Calculate empirical formula, like we said. Work out the ions, work out what B and C are, and write the equation. Okay, right, so let's do this empirical formula first. Let's do this in order. Just go down and tick these things off. So, empirical formula, right, what have we got? We've got nitrogen, which is 11.11%. We've got hydrogen is 3.17. We've got chromium is 41.27. And we've got oxygen is 44.45%. Right, and remember here what we're going to do is divide these by the atomic masses, right? So that's going to be divided by 14, that's going to be divided by 1, so that's going to be 3.17. That's going to be divided by chromium, I don't know off the top of my head. Chromium is 52. And that oxygen is going to be divided by 16. Okay, so let's work all of this out. So, 11.11 divided by 14. Let's call that 0.79. 41.27 divided by 52. 0.79, okay, so that's nice. 44.45 divided by 16 is 2.78. Let's call that. Okay, so then here we're going to divide by the smallest one, aren't we? So we're going to divide these all by 0.79. So that's going to give us a ratio of 1 to something to 1 to something else. So let's do that number divided by 0.79. What have I done? Let's do that again. 3.5. Oh, that's annoying, isn't it? And this one was 3.17 divided by 0.79. And that comes out as 4, essentially. Okay, so therefore that's going to give us 2 to 8 to 2 to 7. So what does that give us? That's N2H8 Cr2O7. Okay. Well, these should start ringing a bell then. Let's go back and look up here. Calculate the empirical formula. Right, we've done that, haven't we? Deduce the ions that make it up. Okay, let's do that now. this should look familiar to us. Cr2O7, we know what that is, don't we? That is our Cr2O7 2- dichromate ion, which actually makes sense. If we go right back up here, it said it's an orange ionic compound of chromium. Yeah, and we're familiar with that from organic, aren't we? You get this colour change of orange to green with dichromate ions. So that fits nicely. So therefore, if that's 2-, this has got to be 2+. So we've got what? N2H8 2+. That's not a thing that we've ever heard of before. What this is 2 lots of NH4+, it's ammonium ions. Yeah. And that's just come from, a bit of background knowledge of I've seen this before. I've never seen this before. I have seen that before. Okay, so this is ammonium chromate then, essentially. Right, so we've done that. Now we need to identify substances B and C. Okay, hopefully I've left myself some space here. So substance B is an oxide of chromium with a molar mass of 152. Okay, so if it's an oxide of chromium, then it's just going to be chromium and oxygen, right? We know that chromium is 52, and we know that oxygen is 16. So if it adds up to 152, it's going to be 2 chromiums, isn't it? 3 lots of 52 is going to be too much. So we do that times 2 is going to be 104, isn't it? Yeah. And so then 152 minus 104 is 48. And then 48 divided by 16 is 3. So this has got to be Cr2O3. So that's my oxide of chromium. C is a gas, and it says each cubic decimeter has a mass of 1.17 grams. Okay, so therefore it's 1.17 grams per decimeter cubed, right? What else do we know? Well, this at room temperature and pressure thing is a clue here. If we're talking about a gas at room temperature and pressure, then we also know that it's 20. What am I writing? It's 24 decimeters cubed per mole, isn't it? Okay, 1 mole of a gas is 24 decimeters cubed. So what can we do with that? If we have that piece of information as well, then hopefully you can see by the units here, if I multiply these 2 bits of information together, the decimeters is going to cancel each other out, and I'm going to be left with grams per mole, which is what I want, isn't it? Okay. So let's do that. This is where the units is really key, right? So I always go on about make sure you're writing down units for things, because you can then see what you've got to do. Okay. So 1.17 times 24. So that gives us 28.08 grams per mole. Right, so what is this then? This is some sort of gas, and it's coming from the decomposition of compound A, right? So it's coming from the decomposition of ammonium dichromate. We start trying to write this equation, actually. We know we've got, so our thing is going to be NH4 2 Cr2O7, and it is just decomposition, isn't it? Yeah, it's not breaking down to make anything else. It's not reacting with anything, it's just breaking down. We know it's making Cr2O3. Right, so that's already telling us that our gas here, it's got no chromium in it. That's already sorted. And if we go up here, it's saying the decomposition made 3 products, B, which we know is that. Let's say that's A, that's B, plus C, and water. Okay, so we know it's making H2O as well. Okay, so something's got a mass of 28. Then what this is going to be? This must be N2, nitrogen gas. Okay, nitrogen's atomic mass is 14, and then this is going to work out nicely. Look, so that's my 2 nitrogens from there, and then I've got 8 hydrogens left and 4 oxygens left by the time I've taken the 3 oxygens off of there. Okay, so that's going to give me my 4 H2O, and that should be it. Okay, so a lot to do in that question. And there's quite a bit there that I think sort of comes from background knowledge, where you're going, oh, how did I work this out? That's just sort of, once you've seen enough of these kind of things, you go, oh yeah, I can see where that's coming from. And same here on 28, that's going to be 2. I mean, this could have been some combinations of oxygens and hydrogens as well, but trying to find something that adds up to 28, 2 lots of nitrogen is the easiest way to get there. So yeah, a little bit of sort of thinking outside the box as well, I think, with that one. Okay, but hopefully you can see where most of that has come from, and even if you're looking at that thinking, gosh, I'm not sure I'd get 8 marks there, at least there's a decent chunk of marks, hopefully, that you would be comfortable getting. Okay, moving on then. I've got a few more questions here. Right, we've got this thing, chromium picolinate. I mean, these questions are all just things you've never seen before, but that doesn't mean we can't do them. This is a bright red complex used as a nutritional supplement. Okay, it's oxidation state +3. The picolinate ions act as bidentate ligands. Okay, that's what it looks like. It exists as a mixture of stereoisomers. Okay, what is meant by the term ligand? Okay. This is the thing, you get this whole information and go, oh, what the hell is it? Oh, what's it? Oh, I know what a ligand is. So don't trouble yourself with all this information unless you actually have to. Okay, a ligand is a species, let's say. I was looking for the word. We can't say ion, we can't say molecule. It could be, let's just say species. It's a species that donates a lone pair. Donates a lone pair of electrons to form a coordinate bond with a transition metal ion. Okay. How is this able to act as a bidentate ligand? So that must mean that it's donating 2 lone pairs of electrons. Okay. The picolinate ion donates 2 lone pairs of electrons to form 2 coordinate bonds. To form 2 coordinate bonds to a transition metal ion. So where's that going to come from? Yeah, if we look at this structure here, I think they're going to want us to specify, because there's potential options here, right? We could have a lone pair from this oxygen, we could have a lone pair from this oxygen, we could have a lone pair from this nitrogen. Okay. So actually it could be any of those. I was trying to work out which is most likely, but yeah, it could be either of those. Oh, and I'm looking at the mark scheme here in the background. I'm looking at this going, how would you know which one that's supposed to be? I think perhaps you can argue it's less likely to come from this nitrogen, because that if there's a lone pair of electrons on that nitrogen, they're likely to be sucked into the benzene ring. Okay, they're going to add to they're going to delocalize, aren't they, into this benzene ring probably. So it's less likely to come from there. But looking at the mark scheme, they will allow you to say, if you've said that, they will give you the mark for that, because it's not, it's not a ridiculous thing. That's definitely a possibility, but it's probably less likely. It's more likely to come from the 2 oxygens. So let's just put that in. The 2 lone pairs come from the 2 oxygen atoms. They do very often like you to say where they're coming from, just so that they know that you understand the structure. But it's nice to see they would give you a mark if you'd said 1 oxygen, 1 nitrogen. It'd be these 2, right? It wouldn't come from these 2. Oh, mind you, that could spin around here, couldn't it? So actually, yeah, it could be any combination of those. But yeah, the 2 oxygens is the most likely, because this lone pair would delocalize into this benzene ring. Okay. Right, and then finally, why does this thing exist as a mixture of stereoisomers? Draw diagrams of the stereoisomers. Okay, so we've got 2 options here. This stereoisomers, it could be cis and trans, or it could be optical isomers. Okay, So we need to work out which this is going to be. We've got 3 of this bidentate ligand. Okay, so if we've actually only got 3 ligands, right? So we can't have cis and trans isomers of these 2 isomers are here, because there is only 3 of them, and the 3 ligands are all the same as well. So you can't have, these 2 are here and the other 2 ligands are they're all the same ligand. So therefore it can't be that. It's going to have to be optical isomers. Okay. So then we want to draw this out. It's going to be a bit awkward to draw, isn't it? But we've got 3 bidentate ligands, right? So therefore it's going to be this octahedral geometry that we've seen before. Okay. And we know what that looks like, don't we? As I said, I always start by drawing this out. So you've got the 2 ligands at the top and the bottom. We've got 2 ligands in the dashes, and then 2 in the wedges. I still can't draw these wedges very well, despite practicing this for years and years. Right, and so let's say that we're going to do it from the 2 oxygens, like we said. This is going to be awkward to draw, isn't it? So I'm going to have my oxygen atoms everywhere. Let's do it that way. Right, and then these 2. So let's put this carbon in the middle here. Okay, we have a double bond there, and then that's going to go to our ring here. Where's the nitrogen? Carbon goes to there. So there's nitrogen's going to be here, like that. Then these 2 are going to be connected. Let's have a double bond off of here, like that. And this is an awkward bond angle, but I don't really want to come down onto the lines here. Oh, this is a nitrogen, isn't it? There's nothing coming off of our benzene ring, no. Let's do that. And then these 2 again, let's have double bond to a carbon, nitrogen. That one, and that one. So that's not much fun to draw. And now we just want to do the mirror image. So again, let's just have our octahedral geometry and worry about putting some stuff on in a minute. Let's put all the oxygens on. So we've decided that they're going to be oxygens. And now we just need to have them in the opposite positions, or mirrored positions to where they were before. So I had the top and then this wedge, so that's these 2 are going to have to be connected together. So let's have that come into a carbon that's to there, and then this is going to this. It's not a benzene ring, is it? Because it's got a nitrogen in it, but it's very similar. It's an aromatic structure of some description. And then these 2, the double bond here. And then these 2 here. One, 2, 3, 4, 5, 6, yeah. Okay. Right, and it does want us to explain a bit as well, so I think we can say this complex has optical isomers and that's actually all it wants us to say. But we can describe them, which are non-superimposable mirror images. It just shows that we know what they are. Okay. Don't worry too much about, drawing these perfectly and go, well, it's not a perfect mirror image. So you've got the right things in the right places. Interestingly, looking at the mark scheme, now I'm kind of surprised that they didn't say this in the question. They've actually allowed you just to do. I'm going to draw this up here so you can see. But the mark scheme actually says that you can just join them up like this and go, these 2 are joined together, these 2 are joined together, these 2 are joined together, and then do the mirror image of that, rather than actually having to draw this out. which I'm kind of surprised by, because I feel like if they were going to let you draw it like that, they should have said, you may represent this ion as this, and then people would do that rather than trying to draw this horrible thing. But just to show you how this would work, then these two would be joined, these two and those two there. And they would actually let you get away with just doing that. But I think I wouldn't want to do that unless the question had specifically told me you can draw it like this. Because you don't want to go, oh, this is easy, and draw that and then lose marks because they were expecting you to draw it properly. That would be really annoying. So yeah, that's a bit of a dodgy one, I think. I wouldn't do this unless they've said that you're allowed to. I think on the modern papers they usually do show you if they're allowing you to represent in a simpler way.